everybody, and welcome to our reInvent presentation on ML Ops at Amazon, where we'll be talking about how to productionize ML workloads at scale. My name is Kieran Kavanagh, and I'm a Principal Solutions Architect at Amazon Web Services. I specialize in machine learning, and working on the Amazon account, I get to work with teams all across Amazon who are using AI ML for all kinds of interesting use cases. I'm here today with two internal customers of mine, Iman and Paul. Iman, would you like to introduce yourself?
Thanks, Kieran. Hi, everyone. My name is Iman. I'm a principal engineer in Amazon Search, and I'll be telling you guys a story about how we scaled one of our machine learning use cases using machine learning operations best practices. And here is Paul.
Hi, everyone. My name's Paul. I'm the Director for Global Transportation Technology Services. I head up a team that builds operational tools to help transportation execution teams to manage the huge transportation network that Amazon owns. I'm here to talk a bit about our experience with ML Ops and some of the use cases that we use machine learning for.
Thanks, Iman and Paul. Let's take a look at what we'll be discussing today then. First of all, we'll talk about some AI ML use cases at Amazon, and then we'll talk about ML Ops concepts, and we'll take a look at the kinds of steps you'll find in most typical AI ML projects. Then we'll dive into actual real-world ML Ops use cases from within Amazon, and then we'll wrap it up with a conclusion. Starting off with some AI ML use cases at Amazon then. AI ML is actually used for lots of different reasons all across Amazon, and in today's presentation, we'll mainly be focusing on the Amazon retail business, which involves everything that's involved in when you purchase something on Amazon.com and getting that product out to your doorstep. Now, take a moment to think about all of the steps that are involved in that process. I won't keep you waiting too long. We are going to take a quick look at it here from a high level. So this is what happens when you buy something on Amazon.com. The process begins with the customer, of course, browsing to Amazon.com, and then you choose a product that you like, you purchase that product, and then somebody in one of the fulfillment centers will pick and package that product to have it shipped out and delivered to the customer. Now, this sequence of steps is going to frame the structure of our presentation today. So as we go through our presentation, we'll be following this journey of everything that happens from when somebody buys something on Amazon.com to when they actually receive that product. Now, take a moment to think about which of these steps is using ML to optimize it in some way. Well, the answer is all of them. It all begins when you browse to Amazon.com. You will see recommendations for products that you may want to purchase based on a number of factors, such as things you've purchased in the past, for example. Also, as you browse around, you'll see these estimates of when these products will arrive at your doorstep if you purchase them. Now, how does Amazon do this? How do they know for all of the millions of products that they have in their inventory and all of the millions of customers that are shopping on their website every day, when each individual product would arrive at each individual customer's doorstep? Well, the answer is they're using machine learning to do this, and it's very much related to Amazon's supply chain. What you're seeing here is a high-level conceptual overview of the supply chain. In reality, it's a very vast and complex network all over the world. And a little bit later in our presentation, Paul will be talking about that complexity in a bit more detail. But just at a high level here, the process begins with forecasting. Amazon uses machine learning to predict how much of each type of product they should purchase and where they should store those products in each of their fulfillment centers around the world. And this is very much location specific. So the kinds of things that are popular to purchase in India right now may be very different from the kinds of things that are popular to purchase in Argentina right now. And it also depends on time of year. People purchase different things in summer versus winter, and fashion trends and lots of other kinds of factors that influence these decisions. And when you consider that Amazon needs to do this for approximately 400 million products every day in more than 150 countries around the world, and all of the things that are required to move these products around and actually get them to customers, you can imagine this is a very, very complex process. And it would not be possible to do all of this without ingesting enormous amounts of data from all over the world and processing that data and feeding it into machine learning models to optimize each of these steps. Now we're going to zoom in on the fulfillment piece here, which is the final step in the process of actually getting products out to customers. We're going to take a look at what's happening inside the fulfillment centers and how AI/ML is being used to optimize the processes in there. One of the first things you'll see in this picture is that there are these mobile shelving units, and products are stored randomly in those shelving units depending on what people are purchasing. And there are also these robots that are moving these shelving units around the place. Now, computer vision is used to track each product, where it is located in each bin as it moves around the warehouses. As you can imagine, it's really important for Amazon to keep track of every product and where it is at all times. And also, machine learning is used for mapping out the path that each robot takes to move things around as efficiently as possible, make sure that the robots don't run into each other. It would be very inefficient if they ran into each other and knocked all of the products all over the warehouse floors. And also, even when these shelving units arrive at a customer's at an employee's station for them to pick the product and put it into a package for the customer who ordered it, it would also be very inefficient if they had to search through every bin here to find the product that they're looking for every time. And computer vision and machine learning are used for highlighting the bin where the product is that the person needs to pick for the order that they're working on. So it makes all of that process much, much more efficient. And this is how Amazon gets products out to customers as quickly as possible. And even the packaging that the employee here will use to package an item for a customer, even that is optimized via machine learning. And what I mean by this is that up until a few years ago, pretty much everything you would have purchased on Amazon.com would have arrived in a cardboard box. And nowadays you will still receive some items in cardboard boxes, but it depends on a number of different factors. It depends on size, for example. Large items are still likely to come in cardboard boxes. Also, items that are fragile will require additional packaging materials to keep them safe in transit. And there are a number of other factors that are used to determine this, but basically lighter and less fragile items are likely to be shipped in these more lightweight products, or more lightweight packages that you see here. And why is this important? Well, machine learning models are used in the fulfillment centers to make these decisions for all of the millions of products that are passing through the fulfillment centers every day. And when you consider that Amazon delivers more than 10 billion items to customers every year, this is really important for a number of reasons. The most important one being sustainability. Sustainability is a major priority for Amazon. This is why Amazon pioneered the Climate Pledge, for example. And if we take a look at some of the results from using machine learning to optimize this packaging, just last year alone, the machine learning models determined for approximately 125 million customer deliveries that no additional packaging was needed at all, because they determined that the packaging that was used from the original manufacturer to send that item to Amazon was sufficient to send that item directly out to customers. So no additional packaging was used. And this optimization last year led to a reduction of about 9,000 tons in waste. And just to put that in some context for you, that's approximately how much the Eiffel Tower in Paris weighs. AI/ML is also used for many other reasons throughout Amazon. If we look at the physical stores, for example, Amazon Go stores allow customers to go in and pick out whatever products that they like, just put them in your bag and walk right out the door, and you don't need to queue up and pay the cashier or anything like that. So it makes it really, really efficient for people if you're in the city and you're on the go. I know that I often use these when I'm walking between meetings, when we actually are usually in the offices, if I want to grab a quick snack as I walk between buildings, for example. Also, many of you will be familiar with Amazon Alexa. Alexa uses machine learning to understand what you're saying and how to respond to you. You can also use Amazon Alexa to purchase things on Amazon.com, and it will kick off that entire process that we just talked about a few moments ago. And depending on where you're living, you can actually have those items delivered to you via drones. And the drones use machine learning to map out the best path to get to each individual customer. Now, we've talked about AI/ML and how it's used in some cases at Amazon. It's actually used for lots more use cases than this that we wouldn't have time to cover all in one session. But now I want to switch gears and talk about how Amazon gets machine learning models into production and updates them as quickly as possible to cater for all of the kinds of workloads that we've talked about. And in order to begin this part of the discussion, I want to take an analogy from the automobile industry, because it's really interesting to see that most industries go through a similar kind of pattern as they begin and as they evolve over time. Now, take a minute to look at what you see in this picture here, all of the different kind of items that you see. Well, we can see a wagon wheel, and we can see some tools and stuff. So this is a workshop where some people are going to build a wagon. And if we look at some of the characteristics of this, well, it's a small space, and it can't cater for more than maybe a few people working together, a small group of individuals working together on the product. And they're going to be using random different tools that they've chosen, but it's not really easy for them to collaborate with people outside of this and to collaborate at scale. So you can have a small group of people collaborating on something, but that's about the limits of it. And it's really difficult to scale these operations out then. You're not going to be creating hundreds of products per day in this workshop, for example. And what the automobile industry did is they came up with the concept of the assembly line. And what you see happening here is that the parts and the tools that people are using to build the products have been standardized. They also have this automation process that allows more and more products to be created more rapidly. And you can see that there's the possibility for many more people to collaborate together on creating these products. And over time, companies want to standardize and automate more and more as much as possible to make every step of the process as efficient as possible. And we've also seen this kind of happening in the software development industry. Most companies, when they begin developing software, they will have individuals writing code on their own machines and then sharing code in various ad hoc ways. I personally have worked on projects at previous companies where we were sharing code via USB drives, for example. But most companies, as they mature their software development process, they want to standardize and automate every step in that process as much as possible, moving to a DevOps approach, for example. And I'll actually go straight to DevSecOps, because even DevOps is kind of old news nowadays. Basically, what you're doing here, you're standardizing and automating every step, and you're also standardizing and automating security measures into every step in the process so that it doesn't come as an afterthought. Now, how does all of this relate to machine learning? Well, in order to talk about that in a bit more detail, we're going to take a look at the kind of steps that you encounter in most machine learning projects. Pretty much every machine learning project begins with you needing to collect and prepare data. That's what your models are going to learn from, for example. And you will often want to visualize your data in some way. You'll want to see what kind of statistical distributions are there in the data. You'll want to see if there are missing values. And you just want to get an understanding of what your data looks like. If you're using a supervised machine learning algorithm, then you will need to label that data, because that's what your model will learn from. And throughout every part of this process, whether it's collecting data, visualizing it, or labeling it, you will want to be checking for bias. And also even later, when it comes to training machine learning models and evaluating them, you want to check at each step whether there is any bias creeping into the process here. You will often want to convert your raw data to specific features for your models to learn from, and you'll want to store them somewhere so that you don't have to recompute them every time. Of course, you need to pick an algorithm. There's lots of different algorithms for different use cases, and you will eventually train your model. You will often need to play around and tune some hyperparameters. These are parameters that affect the performance of your model and they affect your training outcomes, but they are not parameters that are in the data set that the model is learning from. These include things like learning rate and number of epochs, and they differ depending on what kind of algorithm you're using. Now, when you've done all of this and you have a model that you're happy with, you're going to want to deploy that to production so that your clients can interact with it. And you're going to want to manage that and monitor it over time to ensure that it's consistently meeting your business needs. Now, as most companies begin to implement ML projects at the beginning, they will often be doing these kinds of steps in very ad hoc ways. These steps will be usually individual steps that different people in the team are performing using random different tools that they've chosen, maybe based on where they worked in the past or what kind of education they received when it comes to developing ML workloads. And there's not a lot of standardization that happens. This kind of brings us back to this workshop analogy that we had a few moments ago, whereby you can only have a small group of people working together to create a product. And there's generally not a lot of collaboration going on across the company, for example. You may have small groups of people working on individual projects, not a lot of collaboration going on. And also, it's really difficult to scale out your operations when you are working in this kind of way. So most companies, over time, as they mature their ML development processes, they want to automate everything in here as much as possible, similar to CI/CD for regular software development. And this is why last year at re:Invent, SageMaker introduced SageMaker Pipelines. And just a quick overview of what it does, it basically allows you to define your workflow using the SDK, and it allows you to automate every step in a machine learning project. And this is actually an example workflow. This is a real snapshot from the UI for SageMaker pipelines. And what we're doing in this workflow here is we are pre-processing the data before training a model. And then we want to evaluate that model against some metric. In this case, we're using the mean squared error. So this is a regression problem that's being worked on here. And then if the model passes evaluation, you want to register that model to use it thereafter. And also in this case, we're also creating a model so that clients can interact with it. And we're also automating a batch transform job to get predictions from that model. Now, what's really great about automating everything like this is that if I or somebody on my team wants to change anything in this entire process, whether it's how we're processing the data, how we're training our model, how we're evaluating our model, we can make those changes and very quickly automate all of the steps from start to finish again. So it makes it really useful for collaboration and for experimentation and seeing how each little change that we're making affects our end model. And now that we've covered the AI/ML use cases and ML ops concepts, it's time to start diving deep into specific ML ops workloads at Amazon. And with that, I'd like to hand it over to Eamon to talk about Amazon Search's use case.
Thanks, Karen. Hi again, everyone. So I am not an AWS employee. I work for Amazon.com, and I work on Amazon Search. I'll be spending the next few slides talking to you about one of our machine learning use cases, some of the key pain points we had while scaling and productionizing it, and how we re-architected our system to scale and solve the pain points using MLOps, the MLOps concept that Karen covered earlier in the talk. So, to no one's surprise, the use case here is search, but more specifically, it's the relevance of search results. Amazon Search is responsible for the search and discovery experience on the Amazon website. How many of you looked for something on Amazon? I'm sure many of you did. If you as a customer ever searched for a product to buy on Amazon.com, then you must have used our features. But the question is, what's really happening in the background to enable this experience? Our catalog has billions of products. This is huge. Can you imagine that? When you look for something, we cannot check every single product to see if it matches your query. At high level, we start with building an index for all our products. We then look at your search query and use different approaches, including machine learning, to match those relevant and/or interesting products to your query. We then rank them and finally show you the results. So let me show you an illustration of this flow. As I said, there is a matching phase followed by a ranking phase. At high level, our product search engine comes up with all what we call a match set. This match set then passes through stages of ranking, where the top results from the previous stages get re-ranked until the most relevant products are finally shown to you. I actually work on both matching and ranking problems, but who cares about ranking? Let me just focus on the matching part. So we actually use different approaches for matching to come up with that match set. Imagine, for example, that you're looking for a query for burgundy jogging shoes. There is behavior data matching. If other customers who were looking also for burgundy jogging shoes ended up buying a product, then we include it in that match set. There is also keyword lexical matching. It uses the index to return products with keywords in your search query. In this specific case, it's burgundy and jogging shoes. But both of these approaches on their own have their own shortcomings. For example, imagine if there is a new sneakers product and the query is jogging shoes, then there is no chance for the sneakers product to show up because there is no direct keyword overlap. In another scenario, if all the jogging shoes in the catalog are described as sneakers, then the same query may not have a big enough match set. So to solve this problem, we use what we call semantic matching. It's a machine learning approach to find those semantically related products from our catalog to augment the results. So the use case becomes semantic matching, and the goal becomes, okay, I have a query. I want to maximize the similarity between the customer query. Say in that case, I'm looking for a red dress. and those products that I may likely purchase. For example, these two red dresses. But at the same time, I want to minimize the similarity between the query, red dress, and other products that are not relevant. For example, I don't want to see a black dress, a pair of burgundy jogging shoes, or a TV if I'm looking for a red dress. And I'm going to actually skip over some of the details here in the interest of time. But the way it works, it basically maps both the query, in that case, let's go back to the example of burgundy jogging shoes, and the product data. So say, for example, for a product Nike red outdoors running shoes, and then it maps both of them to a shared word embedding space. It then uses a cosine similarity as the distance metric between every product and the search query. There is an underlying machine learning model here that's based on a deep learning neural network model that has a very large number of parameters and gets trained with a very large amount of data. So it is actually a big scalable problem. All right, so I've been talking high level about search matching, and now let me jump into some architecture diagrams. Our science team started with a simple control and data planes architecture where they process the model training data on an EC2 cluster. They then build a custom model, training image, they train that model and dump it in S3. They used a bunch of scripts that they seemed to do the job at the time. So what were the problems with what the science team did? If you were paying attention, and if you remember Karen's earlier slides about modern ML ops and how it actually evolved over time, you might have seen this one coming. Basically, the approach the science team took kind of worked for some time until they had to make a change. Then they had to make another change. They had to add a feature, and then they needed to scale it to more data. They found a bunch of bugs, and so on. And eventually, it went out of control. They eventually hit what we call the tech debt problem. Every new member or a new team would actually build other custom code because they don't really understand what the original code was meant to be. They just copy paste it and start adding more features to it. And this is definitely a recipe for a disaster. It causes a lot of duplications, which makes it hard to debug and difficult to scale any use case. This also results in very limited agility because there will be a lot of manual work and babysitting of pipelines and so on. And that would result in very slow iterations. Any new feature will take a very long time to actually be able to launch. And on top of this, there's a huge operational risk. Remember, these scripts were completely random, built over time. They kind of worked at some point, but no one really understands what's going on. So if there is an issue, there is no way to troubleshoot. So we decided to make a generational investment and update this infrastructure to address the tech debt and follow ML ops concepts and pipelines that we just described earlier in the talk today. So let's deep dive. Let me walk you through the pipeline stages. You may have seen similar workflows to the one I'm going to describe today, because it's actually a typical ML ops one. It starts with a scientist trying to do some exploratory work. So what they do, they look at the feature store, they extract some features that are coming from some data pipeline in the background. They then analyze this data, they prepare it, they pick an algorithm, and they start training their model. And then they actually evaluate and validate the model. They analyze it, they look at the results. If it doesn't look satisfactory, then they keep going into the cycle for a few times until they are happy with a trained model. And then they push the code for the trained model to a code repo, and it starts making its way into pre-prod and prod. So in a pre-prod stage, we actually repeat the same exact steps. And then once we are happy with the trained model, we register that model. We add a bunch of metadata for how this model was actually produced. So in case there is an issue in production, we are able to reproduce the issue and to troubleshoot it. And then we push this model to the production inference point. And then once it's in production, we also have a bunch of monitors to actually keep track of the health of the trained model on a regular basis. And we also use the customer interaction data to actually refresh the model on a regular cadence, say every day, to make sure that it's fresh and it's actually ingested with the latest customer behavior data. So to enable this workflow, we modernized our architecture. We continue to use this control plane and data plane architecture, but we actually evolved it into a more sophisticated architecture. We added an API for our users to interact with. We mapped the workflow to step functions that can be scheduled based on events, and we also leveraged SageMaker in the background. We continue to use S3 and added ECR repo as our data plane for the data and the model artifacts. And we also operationalized the pipelines, added lineage information, added monitors, and added alarms. So what was the result? The result was we were able to save 20% of the time the scientist team used to actually spend on deployments and on maintenance effort. And this is just for one model. Imagine we have many of these models in production, so these savings actually get multiplied. Our science team productivity, of course, also improved by at least 10% because they didn't have to spend that time on babysitting and manual work. And as a result, we were also able to improve our experimentation agility by orders of magnitude. But here is the most important thing. For me, I can sleep better at night, knowing that the best practices, monitors, alarms, resilience, all these concepts that we covered earlier are actually built in. And remember that we use SageMaker in the background as our underlying infrastructure. That enabled us to actually leverage SageMaker features, the ones that exist today, and also any other ones that they are going to launch in the near future. As a result, scaling became a much easier exercise. We can scale to more countries, we can scale to new models, and we can even scale to new use cases almost out of the box. Remember that ranking use case that I skipped earlier? Now that we have the experimentation and the deployment pipelines and the feature store built in, we can easily build and integrate this a new model for this ranking use case. So we can actually rank the match set and return you the best, most relevant results. And that's the end of my Amazon search use case. Now let's consider that you searched for something on Amazon.com and you decided to buy it. Paul's organization is responsible for optimizing how these orders get delivered to the customers. He is going to talk to you about how his organization implemented MLOps workloads. And with this, I hand it over to Paul.
Okay, thanks very much, Eamon, for all that really interesting information about the search use case. Now I'm going to talk to you about transportation. So you've heard all about what happens, in order to make your order and how we find, the right products and things for you. Now I'm going to talk to you a bit about how we get your order from our warehouses to your door. So here what we're doing is we're looking at a mini version of Amazon's supply chain and transportation network. Actually, for all of the techie people here, this looks a bit like a neural network, but actually it's a kind of mini version of Amazon's network. Before we get into kind of the ML stuff and the ML ops aspects of what we've done and our experience there, I wanted to talk a little bit about just the problem space and some of the challenges that we face and why we actually feel that we need to use ML. So here we have the network. Let's start with a question. And there should have been a clue earlier in the presentation, so if you were paying attention, you should already know the answer. How many packages did Amazon ship? Well, if you said 100 million last year, then you would be wrong. If you said 1 billion, you'd still be wrong. If you said 10 billion, you'd be getting very close to the mark. Now, 10 billion packages, that's a lot to ship. So let's talk about the size of Amazon's network. I'm going to ask you another question. How many different warehouses do you think Amazon has in its network? Well, if you said 100, you'd be wrong. If you said 500, you'd be wrong. If you said 1,000, you'd be getting close. Now, 1,000 doesn't seem like very much, right? We just talked about 10 billion packages. But when you think about the number of combinations and the number of routes that can possibly happen through there, then you start to see it's actually quite complicated. And in reality, that's just the Amazon-owned buildings. It's not the vendors and the sellers and all the other different third parties that we're connecting with that also form the millions of routes that we actually have to use to get to our customers. So, challenge number one, just sheer volume and size and complexity of the network. Challenge number two is it's constantly changing. Every single year, Amazon's network is growing, and it's growing quite significantly. Can you guess how much? 5%? 100%? Well, actually, it's about 20 to 30% growth year over year. If you thought it was 100%, then that's, it's a huge estimation. But actually, it pretty much is every 2 years. If we grow by 30% every year, then we're basically doubling the size of our network. So you can imagine at a certain point in time, this just becomes, really, really difficult to manage manually. Okay. So now we've got challenge number one, which is, volume and size and complexity. Challenge number two, which is constant change and constant growth. Then we've got the other aspect of what we need to do, which is we have to constantly evaluate which is the best route to get to the customer. And there are lots of them. And that involves billions and billions of combinations every single second, right? We even talked about search. Imagine if we're going to make a promise to you as a customer to tell you that we can get something to you on time, then we need to be accurate. And so that's billions of calls to transportation systems to find out what exactly is happening. So at a certain point in time, this is no longer a human problem. So I want to talk to you, before we get to the ML stuff, a little bit about our goals. Okay, so we know about the network, we know about the challenges, and I wanted to read to you a quote from Jeff Bezos. It's impossible to imagine a future 10 years from now where a customer comes and says, Jeff, I love Amazon, I just wish the prices were a bit higher. Or, I love Amazon, I wish you'd deliver a little more slowly. By the way, Jeff wouldn't say that if he was Scottish. Jeff would say, I love Amazon, I just wish you would deliver a wee bit more slowly. So I picked this quote because I think it sums up the essence of the challenges that we're facing in transportation, where you've got a huge network, it's extremely complicated, it's constantly growing, and we have to constantly be optimizing for the customer experience and making sure that we keep prices low and that we deliver as fast as possible. So a little bit more on business goals. Customer experience. Accuracy is extremely important. When you order something from Amazon, you want to get it on time. You don't, you're not happy if you get something late. I know I am not happy, and I'm telling you this, I'm not happy right now because something's almost 2 weeks late. We want to ensure that we can deliver at the speed that you want and as fast as possible. We want to make sure that we are doing it in a sustainable fashion. Amazon's committed to be carbon neutral. And we want to make sure that we do it at the lowest possible cost. Okay, so a lot about business context. I hope probably a lot of you have realized by now that there's plenty of reasons why we need to use machine learning in order to help us achieve our business goals. But let's dive a little bit into them. Okay, by the way, this is not intended to be a machine learning class. This is just to talk about some of the use cases. For those of you out there who are saying, oh, why are they using that to solve that problem? These are just examples of use cases there. It's not exhaustive, and I just wanted to share with you a couple of things that we're using. So we're using time series forecasting. What do we use that for? Well, we use that to forecast volume at a given point in time so that we can decide if we need to order more trucks, to make sure that we don't block the flow of packages in the network, which means our network overall is as fast as it possibly can be. We're using regression to evaluate what we think our costs should be, and then when there's issues or when there's anomalies or outliers, we know when it's time to jump in. We're using things like natural language processing, text clustering, to root cause decisions that were made by operators that maybe led to negative impacts, for example, with carbon, so that we can understand a bit more operator behavior and then start to build automated recommendations and automated actions. And then we're using things like anomaly detection to make sure that we're able to capture structural issues in the network, which maybe, for example, potentially cause us not to be accurate in our promises to customers. Okay, so how were we doing it? Well, I think I like to call it the jack of all trades approach. What do I mean by this? So we were hiring all these scientists to do, a wonderful job building us models and helping us to build more intelligent systems that are able to optimize us for our business goals. But in reality, we were using them for everything and anything. Yeah, data engineering, software engineering, DevOps engineering. The scientists were basically responsible for every single part, from experimentation right through to productionization. Now, clearly that's not optimal, and we knew we had a problem, but we weren't quite sure what to deal with it. Just to go a little bit deeper on that, here you can see, for example, our scientists. Actually, believe it or not, we weren't using SageMaker at a certain point in time, and we were just using other tools like Jupyter Notebook. And then eventually we moved to SageMaker, but SageMaker didn't solve all of the problems for us because we still had to do manual deployments. And then in other cases, we were actually handing off to engineers, or the scientists were playing the role of an engineer themselves, having to learn and use proprietary Amazon tools and services, to build pipelines, to do scheduling, etc., and then eventually deploying. So you can imagine the inefficiencies here and all the opportunity we had to improve, which is why we got interested in MLOps. So with the jack of all trades approach that you have, this is what you get. You get a car. What you want is a Lamborghini, but you get something that resembles a bit of a Lamborghini, but probably got a super fast engine, but somehow it doesn't all work together the way it should. What do you want? That's what you want. You want the super fast, slick, Lamborghini that looks beautiful and does exactly what you need it to do and goes super fast. So what did we do? Well, we thought about, we started to investigate a little bit MLOps, and we started setting ourselves some goals. We want to standardize our production, ML production, and we want to reduce our delivery time. We want our data scientists and any of our scientists focusing on science problems and not engineering and data, transformation and all these other different things. And we also wanted to reuse what we did and facilitate knowledge and code sharing and reusability. So we came up with the idea of getting involved in MLOps. We also thought this is where we could have a flywheel effect. If we can standardize and lower our cost and lower our ability to produce ML models and have it actually solve business cases, then we'll provide more business value. We'll get more participants on the business side, more cases to solve, and then we'll continually grow our adoption, reduce our costs, and you can see how this just turns and it becomes a virtuous circle. And so that's why we got into it. So what do we do about it? We started to work with AWS. Well, what I was going to say, if you look at the slide here, my joke was going to be we hired more data scientists, but actually no, that's not what we did. We worked with AWS and we developed something called the Algorithm Lake. And essentially what we did with the Algorithm Lake was we modularized a lot of the different parts of helping to build and develop algorithms, data transformation, data accuracy and audit, training the models, predicting the accuracy of the models and all these other different things, which then meant developing algorithms is easier, and then we took the algorithms and we put them into a catalogue, a repository, where they can be used by other scientists. And at the same time, all of the kind of pipeline generation and deployment pieces are basically now just configuration. And once that's configured, then we can generate the things automatically, and also other scientists can come along and reuse all that stuff. Okay, a little bit more detail on that. Here you can see we simplified things significantly, so we now have our scientists using SageMaker, and after a bit of configuration is done in the algorithm lake, then the whole thing is basically just generated, and there's no need for any scientist to have any knowledge in engineering or any of these different things. Also, they publish to the repository, so then other scientists can come along and use that for their work too. The results? Well, we're still relatively early in our journey, but the results, we have 10 models that we onboarded within the first month. Now, I can't be very precise here, but it certainly, I don't remember as deploying 10 models in the first month. I think probably we were single figures with a lot more effort and a lot less efficiency. Initially we've gained about 30 to 40%. I still believe that we can get better, and we will get better because of the flywheel that I showed you earlier on. Then, apart from just making our own team more productive, we've enabled other scientists from other areas of global transportation services to be more productive as they reuse and also contribute to the algorithm lake. And then, of course, delivering impact. We've delivered a number of ML use cases, within a matter of weeks, that are actually solving real problems, helping us to achieve all of the business goals that we talked about earlier on. So, conclusion? Well, I hope after you've seen Kieran and Eamon and myself talking, that your conclusion is, I need to standardize and automate right now my ML workloads. It's not a question of if, it's a question of when. Secondly, again, I hope that what you've taken away from this session is we've actually had real measurable results in everywhere that we've done it, and we'll continue to have even more as we go forward. And I think probably the last thing and most important thing is it's absolutely feasible. You can do this as well. My team's done it, Eamon's team's done it, Kieran's been involved in it with his teams and worked with lots of other teams to help them do it. You can absolutely do this. Here's the resources. If you want to go on, if you go on to AWS website and look for machine learning or SageMaker or some of these things, you'll find plenty of documentation there. And then from Kieran, Eamon and myself, I would like to say thank you very much for your time today.